Hi, I want to design my own variable lab supply. Greetings, the Astro 30 here yet again, and this is going to be a series of videos that I'm going to be doing over the course of the next few months, in between other things. Now I want to design and build my own variable bench power supply, and part of the design is going to be based on Dave Jones from EEV Blogs series about 9 years ago on lab power supply design. I will link those videos in the description, but I'm going to do something a little bit different to his design. Now, we need to go through the prerequisites of what I actually want. So these are my prerequisites. I want a constant current of 0 to 3 amps, which is adjustable. So also some current limiting in there. A constant voltage of 0 to 30 volt DC. Remember that. 3, it has to operate from a single supply, so it's not bipolar. And above all else, number 4, it must be a linear supply, not a switch mode power supply, because switch mode power supplies, especially for testing audio circuits, are inherently noisy unless you've got some really good filtering on the output. Plus, switch mode power supplies are also known as the voltage to smoke converters. I don't really like them, but they do have good constant current capabilities and very good regulation. There should be a fifth point here saying it's regulated, but obviously for an adjustable power supply it is going to be regulated. So remember these prerequisites, because now on to my next point. Now most of you would probably say the easiest solution is the good old LM317T. Yes, it is. It's an adjustable voltage up to around about 36 volt DC on the output. However, it has a reference voltage internally to this IC of 1.25 volt. So the lowest voltage you can ever get out of it is 1.25 volt. However, that's not what we want, or what I want. I want it to go down to 0. So the LM317T is not going to be sufficient for that. Also, they have a maximum current of 1.5 amps. So unless you add a series pass transistor here on the input and output, we're not going to achieve 3 amps of current. So Dave's solution was to use the good old LT3080, which is an adjustable regulator from 0, which is what we want, to around about 35 volt on the output, and has a input range of, well, I think it's 6 volt to 36 volt. Now remember, this is just a normal buck regulator, it's not a boost, so if you put 6 volt in, do not expect to get 36 volt out, just saying. So what all it consists of is an error amplifier and a series pass transistor. That's basically it, with the voltage control set pin controlling the positive input of this op amp to adjust its output. And this is configured as a voltage follower, and basically for all intents and purposes it's driving the base of this transistor on, and so that is effectively also an emitter follower. So the way this works is, whatever you set the voltage on this point from, and this is basically going to be a voltage divider here, that's basically a constant current source up here, so there'd be like probably a resistor, maybe a couple of transistors or whatever to do the constant current source here, but that would set up as a voltage divider. Now what op amps generally try to do is it tries to, from the output's perspective, to make both these input pins the same. So whatever you set this pot to and how much voltage is on this pin, say this was set to 1 volt, and there's 1 volt on this positive pin here, there'll be 1 volt on this negative pin here, therefore 1 volt on the output, minus the 0.6 of a volt drop of the transistor, of course. And that's basically how it works. So I could order some LT3080s, and you can put a series pass transistor here between the input and the output if you want to boost the current. These are capable of 1.1 amps. or according to the data sheet, you can actually parallel these up together, 2, 3, 4, however many you want, to get the desired current. So each of these regulators are sharing the load, the current load, equally. So we're not going to talk about current limiting and constant current here for the start. All I'm talking about is the actual voltage control part of it. Now, I don't want PWM control from a microprocessor. It would be nice, but that's added cost, and I'd have to find a processor solution and I'd have to program it. And that sort of stuff I'm not really into. Now, as I said, I could do that and buy an LT3080. They don't sell them at JCar. I'd have to order them and wait around. Or we could just simply, out of an op amp and a transistor or a couple of transistors, we could actually come up with our own error amplifier voltage regulator. That's basically all this is. Alright, I've got the circuit built now and I'm ready to test it. I'm going to change the configuration a little. The center of the pot goes to pin 3, and this potentiometer is wired as a potential divider, so one end goes to negative and the other end goes to positive. So I'm going to power it up now and see what we get on the meter. If I can work these stupid clips, whatever you want to call them. Okay, we've got 2.5 volt coming out, so if I rotate my pot all the way up, slowly, we are getting a voltage increase, There we go. I'm running on a 9 volt plug pack, by the way. And I haven't got the output stage configured, I've just got the output going back to pin 2. So we've got the feedback path there, it's still a voltage follower. 6 volt, 7 volt, 8 volt, and we're maxed out at 8.7 volts thereabouts, so we're probably about a volt less than what the supply can actually deliver, maybe a little bit less than that, maybe about 800 millivolts off. So we'll rotate that back down. Now we'll go down to 0. Oh shit. We cannot get 0. 1.7, 1.8, 1.7. I wish I had a 10-turn pot, it'd be a lot easier. Oh, about 1.7 volts, maybe 1.6 volts. It's as low as it goes, and then it shoots back up to the maximum supply that the op amp can deliver, which is 8.8 volts. So this circuit clearly doesn't work. Why doesn't it work? I don't know. How can we make it work? Sit here and cry? Redesign it? I don't know. So anyway, this was a failed project, so this is not going to work with this op amp. So anyway, I'm going to end this video here on the Astro 30. If you enjoyed this video, please remember to rate no. I'm not serious. This phenomenon that I'm experiencing is actually a well-known phenomenon, especially with the TL07X and TL08X range of op amp ICs. It's just an inherent thing that they do. This is the schematic I'm working with. I haven't got this part in here yet because I haven't got that far, and the output stage is missing. So pin 6 is running directly back to pin 2, so we've still got our feedback loop there as a voltage follower, and I'm measuring the output at pin 6. Anyhow, that's irrelevant. What is happening is a phenomenon known as phase reversal. It cannot go further than 1.6 volt before 0, and then all of a sudden it goes shoom and shoots back up to the positive rail. Why it does that, I don't know. Texas Instruments know about it. They have given in their data sheets on single supply rails the minimum input voltage you can give on these JFET inputs. It affects all the JFET inputs. If this was a bipolar junction transistor input stage here in this op amp, we would be getting to 0, but that's beside the point. Question is, how do we fix this? We need to give this op amp its own virtual negative rail or a negative reference rail, which is separate from this common rail. And there are many methods of actually achieving this, like getting a split supply off of a single supply rail. And no, putting two 10k resistors or 100k resistors here in a potential divider network on pin 3 makes any difference. The pot is already a potential divider. So no, it will not work. So how do we give this a virtual negative reference? Alright, so I've switched over to the 19 volt supply now, and I've removed the negative wire from the ground point or common point. I'll connect up my 19 volt supply, and currently that's not doing anything because there's no negative reference to the op amp. And now I use my 9 volt supply with the negative connected to pin 4, and this positive connection now going to the common point. Interesting. We got 0.33 odd volt. However, I'm going to have to move my ground point for my pot to the actual common, or else this is not going to work. I think that was a common. No, I missed it. Try that again. I think it's that one. And would you look at that? Albeit there's a little bit of a DC offset there of 18 millivolt. It's close to 0. And if I rotate the pot back up, we should see the full 18 odd volt there, minus the volt. Right, we're at 18. And we're at 0. Yay. Alright, so effectively what we have done is we have now connected our, I'm going to represent this as a battery. We have now connected our second battery source with the positive going to common. That will now move, and that will now move. And now we have created a negative VCC line. I've actually done that wrong. That will move. That will now connect to there. And we've solved the problem. But now how do we do this? Well, again, from a single supply situation, it's not really that difficult.
One eternity later.
Okay, so during the making of this video I've killed so many components. That TL071 is that TL072 is now this 50k logarithmic pot is now and this 10k linear pot is now I've now lost $12 worth of components during this experiment. Well, the TL071 is out for two reasons. One, I couldn't give it a negative reference that was separate from the main supply, and inadvertently I actually damaged the IC, so it no longer works. Now I've got an NE5534 in the circuit, and if I play with my pot we can see the voltage output is variable. However, down at minimum I'm still getting like nearly a volt out. Doesn't quite go to 0, and there is an adjustment trim pot here for the DC offset configured how it is in the datasheet, but yeah, I can't get that offset any lower, so that's interesting. If I insert a 10 nanofarad ceramic capacitor between pins 8 and 5 as the compensation capacitor, I am now looking more at 0.888 volt DC out at minimum. So the datasheet isn't really specific on what the frequency compensation capacitor should be. I did have 100 nanofarad in there before, but that made it worse. So for now I'm going to leave it like that, and I might build the output stage so we can actually start loading it. Right, I got the output stage built, but this is not going so well. I think I've damaged the NE5534. Because yeah, I was getting 3 volt at the output. That output transistor was getting hot, and that was with the pot at 0. I got an NE5532 in there, and at full anti-clockwise we're getting 600 millivolt out. Now maybe we can drive a load. So I've got an automotive test light over here. I'm going to hook that up to the emitter of this transistor. And well, we've now dropped down to 0.128 volt DC, which is, yeah, okay, not quite 0. Wind it up. 5 volts, it's starting to glow. 6 volts. However, the maximum I'm getting out of this is 6.61 volt, which is not great. So it is working, but it's not working very well at all. Because if I'm getting a maximum of 6.6 out, I need to know what my input voltage is now doing, which is the collector. I've still got like 8.83 volt there. So yeah, this is just a disaster. Absolute disaster. It's just not functioning the way I want it to. Because unloaded we get the full 8.85, so alright, so through the process of messing around I've actually come to a conclusion that I'm doing it completely wrong. If I connect my test light at 9.48 volt roughly on the output, it stabilizes, but it's still maintaining roughly the right voltage. Now, what is the reason for this now? I've connected a humble 9 volt battery from the positive to the ground point. The negative of this battery now goes to the negative pin of the NE5532, and as a result I get a more stable output. I'm using a 19 volt adapter now, but if I wind the control all the way to 0, yeah, I get 0. So the op-amp's going to have to run on a split supply, so I'm going to need to figure out a way of generating that negative reference voltage for the op-amp to run properly. So one way we can do it, and I'm going to elect to do it this way, is to use a basic like sort of charge pump and shunt regulator with a Xenodiode sort of arrangement, where it takes a voltage off of the secondary transformer winding and it charges up a capacitor on one side of the plate, and then on the other side of the plate you get a voltage being pumped in. So that gives us roughly minus 5 volt. If we look at the meter, and I'll hook up the AC connection, you can see we've got minus 5.2 volt. That's measuring between the actual common rail and the anode of the Xenodiode. I'll show you a schematic later. Okay, I've got that charge pump sort of shunt regulator arrangement hooked up to the negative pin of the IC, and the positive of the IC is connected to the normal positive rail. And I'm going to probably connect up the AC wire directly to the transformer so it's got power there. I'm kind of concerned at this point of powering it up in case I blow another IC, because I don't have any more. But anyway. Well, it didn't blow up. 2.57 out. Rotate my pot. Yeah, well, that failed to work. Alright, now it works. I indeed blew another IC. I will say, when testing stuff, if you're going to leave the negative of your op-amp floating, disconnect the positive so it's not overdriving the op-amp internally. And so we're getting a maximum output voltage of 21 volt. Yay. Would this have worked with the 534, yeah, probably. So that is now working. So I've got 4 blown op amps, which is kind of ridiculous, but yeah, this is what happens. I'll have to check the data sheet for the NE5532 to see what its maximum output range is. We've got a little bit of a drop, but it's not bad. It is actually functioning the way it should. How special. Now, the next thing I want to do is I want to take a few voltage measurements around the circuit. You'll notice I've got the TIP35C clipped with a vice grip to a piece of angled aluminium, which is about 5mm thick, 6mm thick, something like that. Nice, heavy duty. So currently my output voltage is set to 10.72 volt roughly. I'll just introduce my test light. It doesn't actually drop down that much, to be honest. Now that the output capacitor is there and it's bolted to a heatsink, it's not doing too bad. We're only losing about 400 millivolt or something. So I'll wind it down to absolute 0, which is, that's the output capacitor discharging. Got about 2 millivolt there, so I'll put it on the millivolt scale. We've got 3.2 millivolts roughly DC on the output, which is naff all, because as soon as I introduce a load, it'll almost bugger off to 0. So this is why I think the output will need to have some form of load, maybe 1, 2 MA, something like that on its output, constant all the time, just to help it regulate a little bit better and maintain the voltage stability a bit better, so that when you connect a real load it doesn't drop as much. Okay, so here's our completed circuit. Down here is the charge pump I was talking about. It takes the secondary AC voltage from the transformer through this current limiting resistor, and it's basically charging the positive plate of that 47 microfarad 63 volt capacitor, and due to the reactance of the capacitance it actually allows the voltage to pass through. And then this diode here is going to be a half-wave rectifier, which is going to only accept the negative half cycle, which will then appear here. And this is a small smoothing capacitor, another 47 microfarad capacitor, 63 volt, and that's referenced to our common rail. This other diode over here also references the rest of this circuit to the common rail. We've got a 220 ohm resistor, which is a current limiter, going into this clamping 5.1 volt Zener diode, which at the end of this point, this node here is our negative V reference, and it's around about 5.2 volt, roughly thereabouts. And that feeds into pin 4 of the op amp. Pin 8 of the op amp just goes straight to the positive rail. We have a 10K variable pot, which is referenced to the normal common, and that allows us to vary the voltage on the non-inverting input pin 3 here. So whatever is on this pin should be on this pin and should be on that pin. So if this is set for 2 volt here, there should be 2 volt here and 2 volt here, if it was an ideal op amp. It's not an ideal op amp. That then goes in via a 1K3, that's just a base current limiting resistor, into the base of this BD139, which is connected in a Darlington configuration with the TIP35C. You can easily use a TIP3055 there if you want. And the emitter forms our output. Okay, so wind it up to full voltage now, which I'm going to say is roughly around the 19 volt mark. Okay, so we'll remember that figure, 19 volts. So the next thing I'm going to measure is what the DC voltage after the half-wave rectifier is there. So I've got another probe connected to my meter, and the negative probe common is connected to the common point of the circuit, which is negative. We only have roughly 7 odd volt DC there. Of course, at pin 4, we should have R minus 5 volts, which we do. So now let's see what the input pins, pins 2 and 3 of that IC are doing. Remember, output voltage is 19 volt, and that op amp should have 19 volt on both its output and its input pins, because the op amp, remember, will try to do whatever it can to its output to make sure both inputs are the same. As for what the supply voltage is coming in off the collector of the transistor, we've got 21.39, if it will stay on there. 21.45 we'll say. And again, the output is around the 19 mark. This is going to be awfully awkward. Pin 2. We've got 19 volt. Pin 3. Got 19 volt. And of course pin 1, which is our output, if I can get to it, is actually about closer to 20 volt. So I'll just verify that again. Pin 2 is 19, almost 20. Pin 3 is almost 20. So practically speaking, it is keeping the inputs the same as the output to a point. I am actually, tempted to tap over to the other side of the transformer here off the 9 volt winding here, so we have a total of 27 volt AC across it, and see if the circuit will handle it. Probably will. I'm a bit dubious about doing that. So for now I'm not going to do that, because that's my last NE5532 op amp. I don't have any more. And I'm not sacrificing any more op amps today. I've had enough of destroying op amps over the last couple of days and potentiometers. So yeah, there's that. So through all this circuitry, we are actually losing about 2 volts from the supply. That's including the drop of the transistor and, well, all the rest of the other circuitry that's involved, including the resistors. So we know that if we had 22 volt or 21 volt going in, we can expect 19 volt out. So all well and good. That's not bad. It's only a loss of what, about 1%, which is not really that bad for a simple circuit like this. So yeah, it's what it is. Oh, I've also got a 2.2 microfarad capacitor across pin 3 and normal common. That just filters out any noise that may be on the line as you're varying the control. Now, this pot does not have to go to the positive rail. This can actually then come off here and be fed to the constant current amplifier circuitry that controls our current output. We can use this V bias line here if we need to power another op amp and we need to get absolute 0 volt out of it. So we would use that line as well for that. I've actually blown up 3 op amps now. I blew up 2 potentiometers, don't ask me how. I blew up the 50k and the other 10k that I had, and that was because somehow I wired it wrong and I put DC voltage directly across 2 of the resistance pins, like the center and one of the outers, and blew the carbon track straight off of the potentiometer's base. So they're both useless now. Both blew for the same reason, by the way. Alright, without making this video too long, it's already up to the half-hour point now. I know this because I've already edited it. I went out and bought a couple of new NE5534 ICs. Kind of glad I did, because now I've got 5 destroyed op amps there, a TL071, a TL072, 2 NE5532s, and an NE5534. My collection of destroyed parts is starting to mount up. We've got 9.39 volts set on the output, and I also found out that that test light is not really a good load to test on this circuit. I'll show you why. Alright, the circuit's depowered now. I've got the test light just laying across the top of the PSU. Those capacitors are discharged, so it's all good. I've got my multimeter hooked up across the test light in ohms. About 4 ohms. Because I did actually verify that this would run on 30 volts by connecting my 9 volt plug pack in series with the positive wire of this linear supply here. Yes, it does, and I get up to 30 volts output. However, as soon as I connect the test light to the circuit, doesn't matter where the voltage is set on the pot, it could be set down to 1.5 volts. As soon as you connect it up to the output transistor, bang, it goes up to about 18 volt. Yeah, and that thing glows really brightly. Fuck you. So now that we know what the ohmage roughly is, it's saying 3.9 at the moment. We know that the voltage going into it was 18, roughly. Divide by our ohms, that's 4.61 amps of current going through that circuit. And as there's no constant current circuit there yet, or any current limiting there, it's going to quite happily deliver that 4 amps. Luckily these transformers are rated at 6 amps each. And you can see off to the right there, I've got that little mini 100 milliwatt amplifier just sitting there. I was actually using that as a test load to connect to the power supply, because it has a much higher resistance, obviously. And that's how I found out the other NE5532 was Cactus, because there was no audio amplification. When you cranked it up full, it just went distorted, so one channel in that NE5532 is completely f***ed. Anyhow, I've got the DC offset components hooked into the circuit now, and I've got another little addition there too, but for now I'm just focusing on that. I will say furthermore on that little test light that I'm not going to hook it up to the circuit to demonstrate, because things were starting to heat up. I could smell burning resistors. So yeah, the little circuit couldn't handle it to the point, well, I don't see why it would. Something was heating up, I couldn't see what it was. So yeah, test lights are not a good load to test on power supplies, unless it's got good current limiting, of course. Anyhow, I digress. What I want to do now is I've got my multimeter set to the millivolt scale, got the voltage on the circuit set to 0, and I'm going to see if I can trim out the DC offset that's on the output. So we plug the circuit in for the 1500th time, and if we look at the meter there, we can see we've got 6.8 millivolt minus. So I'll just see if I can trim that out by turning the pot. That's obviously the wrong way. I need to go this way. Going down, going down, going down, down. Once I get to a certain point, it should start rising in the positive region. Getting close. Bam, 0 volts. So if I keep on winding it now, we can see that it's now starting to creep up in the other direction, so I'll wind it back down to 0. So I've verified that I can actually zero this out completely. And there we go, we've got 0 volts on the output, which is one of the requirements, that was the wrong way, which was one of the requirements of the prerequisites of the circuit, is to have 0 volt DC output. So the circuit is now set to 9 volt. Now the amplifier is powered up, but I've lost connection. It is oscillating a bit there.
Sisters and my mother. Sisters? Yes. 2 sisters. Yes. They were.
I don't think the TL072 works in that amplifier circuit too well. Also, the voltage is jumping around a bit. Alright, so this is the finalised schematic. I'm not going to go through and explain it all again, because I already have explained it all before, including this circuit down here. That's just a minus V bias, or V reference line there. You'll notice there's a few little bit of differences here. I've got a capacitor on the output, 2U2, and a flyback diode. This diode here discharges that capacitor when there's no output. It just gives the a path for the capacitor to discharge through if there's no load connected. This BC546 here, this transistor is slightly forward biased, and what this is doing is it's providing a small, very small current draw to the output stage. So effectively what this is doing is providing around, I couldn't get precise measurements on this, but around 40 microamps, which is naff all, but it should help stabilize the circuit when there's no load connected. However, I've got the issue of the load not being stable, or the regulation not being stable when the load is varying. Like current is starting to be drawn on the load, the voltage moves all over the place. This is our DC offset adjustment pot between pin 1 and 8, and that just basically enables us to zero out the voltage on the output. So if anyone's got any ideas of how I can make the voltage more stable on this, aside from adding constant current of course, let me know, because it should not be jumping around like that. Maybe I'm not doing something right, I'm not sure. And actually, before I finish this video, yeah, I know I've been saying it all video, I have actually fixed the stability problem. I've got this relay down here and it was doing exactly the same thing. It's a 270 ohm coil or whatever. As soon as you connected it up across the output, that would shoot up to 15 volts. But now, if I touch the output, as we can see, the voltage doesn't change much. I'll disconnect it. I added a 10 nanofarad ceramic capacitor between the pins 8 and 5, which is the comp pins on that IC, and that tends to fix the problem. That's better. And I'll leave you with a clearer drawing of the schematic. There it is there on paper, so it's a little bit more legible. Anyhow, I'm going to definitely leave this video here now. I'm the Astro30. If you enjoyed this video, please remember to rate, comment and subscribe below. And you can always follow me on Facebook and become a Patreon supporter for as little as $1 a month. Links are in the description as usual, guys. Anyway, this is the Astro30 saying, see ya, have a great day. And that took longer than necessary. I've spent the last 4 days faffing around with this.